explaining one problem. The problem is your broadband connections as well as your connection in CHK. Okay. Well, we all know that CHK has the best network utilities, right? What is it? We have a big fat pipe. Okay. The big fat pipe directly connecting to the HKIX. The big fat pipe connecting to every places in Hong Kong, but this is the area in Hong Kong fat. What if we go outside, go to the overseas places where you have to go through much, the bandwidth is like this, okay? And in CHK, the bandwidth is like this. So it's a narrow pipe. Now what is the effect? The effect is as if we are pushing some fluid, okay? Treat this as a fluid. This is what is the color? Maybe blue, okay? The blue color or the green color, okay? As if we are squeezing pushing the fluid into the narrow pipe, okay? Now suppose we are using my MacBook, okay, to push data to you, any MacBook here. We won't experience this. Why? Because we're in the same network. We are from a fat pipe to a fat pipe, and in between is also a fat pipe. So we won't experience this. Now we are pushing data without any delay, right? You push things out. You won't expect there is delay, right? So you keep pushing, so the packets are close to each other. But what if we push into an overseas cable, overseas optical cable? Then we have an illusion that we are pushing in to a narrow pipe. While you're pushing, it takes time, right? It takes time to push something in. So here we will queue up things. So what is this diagram? Actually, this diagram can be how can I say a combined effect of a router somewhere in between, and this is your home. This is your home. So it's just an illustration, high-level illustration of this. Now, while you are squeezing data into this fat pipe, you have to stay there for some packets to store here. So you have a congestion here if the buffer is running out of space. Let's imagine that the buffer here is of infinite space. Okay. So here, what happened in the other end? In the other end, maybe it is going to maybe Google. We go through optical fiber slower than fiber within the cable in the Google infrastructure. So let's say we reach the infrastructure of Google, it becomes big fat pipe again. So what is the effect? The effect is if we need to pull things from the narrow pipe to the big fat pipe, and why we will introduce some interarrival time here, very easy. You are pushing things from, okay, I do the animation, human animation here. You push, okay, that means you take time, okay, take time push, okay, then another push, then another push. So you take time to push it, but at this side, you are pulling, right? You pull one, okay, and then send it out. Now while you're pulling the first one, the second one is coming, yet it takes times. Okay, it takes time for the other side to finish pushing the one that is just pushed. Okay, I give labels. I push the I packet there, I push it here, and I pull the I packet out. While I finish pulling out the entire I packet, send it out to the Google infrastructure, I'm waiting for I+1. And you see that there is no gap inside this arrangement. You see there is no gap inside the narrow pipe, but because the narrow pipe is slow, so as if I'm doing a slow motion. Oh, because it's slow, right? Slow motion, and push to the at that area. And then I pull it in slow motion and push it again. So with this strange, okay, we are enforcing a new interarrival time, although when the same thing's out, there's no intersending time. Right? Understand this effect? And why is it so important to mention this? this is the basis of why TCP has timeout. Right? Very natural. You go through this narrow pipe, introduce the interarrival time, and that interarrival time should be generating ACK with the same interarrival time. Because we treat ACK as very small, so when it push in and push out, it won't introduce any extra slow motion thing. Okay? And it will pass this and another symmetrical networking construct, but very small. And this interarrival time, if it is X, this is also X when it come back. Okay? Now the problem is, I'm a sender. How can I know this interarrival time? Usually it's by hard code. Okay? The first, when it starts in hard code, let's say it's 3 seconds. Okay? And when the other end knows that within 3 seconds, I should have the ACK because of this effect. Okay? Now, what is the problem? Okay, the problem, what if I miss out the second one? If I estimate that this width is 3 seconds, and after 3 seconds we don't receive this, it is a packet loss, and I consider it as a congestion. And this is the high-level point of view of what exactly is a congestion, and Van Jacobson knows about this. The interarrival time is very important. So it invents TCP with a new control. The new control is, now remember, this is interarrival time. Another time I talk about is round trip time. So what does it mean of round trip time? The time I send out things, a packet sent out, and it comes back should be more or less constant. Right? If I go through the same infrastructure and the same infrastructure condition doesn't change. Understand this point? Okay, so this is round trip time, and the round trip time, the duration is totally controlled by this artificially introduced interarrival time. It's kind of the same, plus the distance between these two. Okay? Understand? The distance between these two endpoints plus this introduced interarrival time. So this is Van Jacobson's first observation. And because of this first observation, okay, he used this point to make some really bold, okay? Really bold estimation. The bold estimation is, if I did not saturate the network, so what does it mean of saturating the network? Use up the buffer here. Okay, then it means saturate the network if I use up the buffer. Okay, if I don't saturate the buffer in this area, then I can keep on pushing data into the network. If I found that I saturate the buffer here, then I will find that within that, okay, turn back from one go back to your home, the is round trip time, okay? The round trip time, after round trip time, I miss something. It means that I already overly saturated the network. I should step back, okay? So by using this control, okay, what exactly should TCP do? TCP should first, there are two phases. First phase, try to saturate the network. Because you do know how many people using this pipe. So the first thing is try to saturate it. Try to generate congestion. Once we generate congestion, we back off. Okay? And how to saturate the network? Okay? So this is what we call bandwidth probing phase, or called slow start. We start with slow. Okay, don't think that it's really slow. Later on, you will see that this phrase is crazy. Okay, we call it bandwidth probing. So what is a bandwidth probing? Try to saturate this guy. First, start with one packet. I send out one packet. Okay? And if that packet can safely come back as ACK within the time that I estimate, the estimate is the function time. Within that time, good. I send out another one. Right? I send out another one. This is something wrong with the animation. Later I will tell you what is something wrong because I have the third one here. So the animation come up early. Okay? So then I send out the second one, and the second one should give me the second ACK. Okay? I am not satisfied with this. This is not bandwidth popping. This is just rely on the bandwidth is okay to satisfy one packet transfer. So the bandwidth popping phase will treat ACK as a signal. Hey, come and abuse me. So how to increase the abuse of the network? Okay, from 1 to 2, I introduce the third. And the third is actually the bonus produced by the previous ACK. So let me summarize this bandwidth popping phase. Every time I start with the flow with one packet, and if that packet comes back, it gives me a confidence that I can send out a second one. And the first ACK, when it comes back, because I want to pop for more bandwidth, okay? So I treat the coming back ACK as a signal that come and abuse me. I treat it as a bonus. And the bonus is send out one more. Okay? So what is the ending result? The ending result is grow the network bandwidth exponentially. Why? When this pair send out, it will introduce in the arrival time, no problem. I have a long enough round trip time. Then that's okay. Every time when it come back, okay, I treat every ACK as a bonus. So when I send out 2, come back 2, okay, give me a confidence that I send out 2 more. That is number 4 and 5. Yet, because of these 2 coming back, I introduce for each ACK 1 more bonus packet. So the next round, I send out 4. Next one, I send out 8, 16, 32. Okay? So within several, maybe one packet is 1,000, 1,500 bytes. Within 20 rounds, I can grow the network to 1 gigabit per second. No problem. Yeah. So this is what we call the bandwidth popping phase. Okay? So every time I grow the time that I send out. Now, what happened between 1 and between send out 2, I won't say anything. Because I'm popping the network. I don't know whether I should proceed or not. So the first guy when I send out, I wait until this guy come back. Then the next pair is 2 and 3 send out together. And I will wait until this pair come back. When this pair come back, I will send out 4. When the 4 ACK come back, I will send out 8. But in between, I do nothing. Because I don't know the situation in the network. I don't know. So I just send out and wait. If the number of coming back ACK is not as expected, that means that there is a congestion. Then we will enter another phase. Okay? Before we go to another phase, let me do a summary. The summary is at each ACK arrival, okay, we have some control. So what is this control? CWND. Okay? I should have skipped the name, okay? The CWND. I didn't write down. I didn't write the CWND here. Oh my god. Why? CWND. Okay. Oh yeah, this is first time. How come I created bad notes, huh? Okay. Oh, so what is CWND? Okay. So the CWND is, first of all, it's a kernel variable. Okay. I really copy a kernel code, and this is the expression inside the kernel. CWND means congestion window. Yeah. Don't tell me that Y is a congestion window. C means congestion. WND is window. Okay? I don't know why it's window because WND. Okay? So what is a congestion window? Congestion window is the variable to control how many packets I can send out at a time. So the CWND will grow with 1. With every returning ACK, I will grow the CWND variable by 1. So the first time I send out is 1. When the 1 comes back, I make it into 2. So every time now I can send out 2 packets. When the 2 packets both come back with a successful ACK, each ACK contributes 1. So CWND becomes 4. And CWND will grow exponentially. Okay? And now this is the general rule. Previously we talked about the flow control window. Okay, the advertisement window, the flow control window. The flow control window is to control how can I make use of receiver buffer. Okay? The receiver buffer is called receiver advertisement window, yet the CWND also become a control now. This is something new, okay? And the CWND, I didn't tell you what is the unit. I only tell you that it is packet, okay? It means 1 packet, 2 packet, 3 packet. It actually means CWND times maximum segment size. Every time I send out maximum segment size of amount of data, okay? So there's CWND times MSS, okay? By the way, what is the starting CWND in a real network, okay? You can do a Google, okay? And you will find that Google is suggesting a change. Really, Google is a company, okay? They do many networking things, okay? I remember the original CWND should be free, okay? Should be free, start with the number 3, okay? Google don't satisfy with this, okay? Google think that we can boost the network throughput by having an higher initial CWND. I don't know whether it's being passed or not, okay? But there's something that Google is doing. Okay, so this CWND controlling how many data you can send out. Now, what if I really sense some problem during a talk for network bandwidth? I send some network drop, okay? I send a particular ACK didn't come back. Now I will enter the next phase. What is the next phase? Okay, we know that we become too aggressive. Okay, we consume some buffer and it's running out of space. Then we will enter the next phase called congestion avoidance phase. No longer bandwidth hopping. Okay, so this phase controls something. Control what we call a slow start threshold. Okay, when the slow start is climbing exponentially, there is a threshold. Okay, don't climb beyond that. Okay, if you climb beyond that, we will go into another mode. So what is another mode? Another mode is much slower. From the previous rule, CWND, every time returning ACK, give me 1 bonus, become 1 over CWND. Much slower. It's originally becomes something like this, and then like this. Okay, I can draw it here. Yeah, I know my hand is not good enough. Originally it's like this, and then suddenly it becomes something like this. Have you ever experienced this? Yes, this is your everyday life. When you start downloading something big, the bandwidth growing like crazy. Start with several K, and then grow to several hundred Ks, and then go to 1 megabit per second, 2 megabit per second, and then suddenly flat out. And even don't climb. It's because of this strange control. 1 over CWND, very slow. The bigger the CWND is, the slower the growth rate. Understand this? Anybody know? This is a great invention. If I have a very small CWND, the growth rate is still good, right? If I have a big CWND, my growth rate is small. Understand this? This is countermeasure is countermeasure, is to guarantee one thing. You have a big resource already. Why do you want to climb fast? Right? If you have a big resource already, the growth rate should be lower and lower and lower. If you don't have enough resource, okay, although you enter the congestion avoidance phase, you are being block shot, okay, don't climb, okay. I still give you a higher growth rate because you don't have enough resource. So there's a great invention, great equation here, okay. So understand this, this insight, okay. This is really an insight. Now, when I enter this phase, I will follow this growth rate so that our bandwidth growth will flatten out or very slow, okay? And it can be summarized in this figure, okay? This slow start threshold, no one knows what is the initialization value. Later on, I will tell you why, okay? And this is some of the ending results of a TCP growth. Okay, this is a kind of a, how can I express this? Just like a saw, okay? Just like a saw. What is it? When you kind of grow, and suddenly experience some packet drop, the next control is you will suffer some loss. Because if you don't back off, okay, this is called, we call it TCP back off. If you don't back off, what is the problem? You hope for the bandwidth and you grow too fast. That means that your current rate or your current bandwidth consumption is too high. If you don't back off to some smaller value, you will still experience congestion. So the TCP control has a so-called a very famous phrase, additive increase, multiplicative decrease control, to push down the CWND, to back off to some value. Later I will tell you why you back off to that particular moment. Back off to some value, and then start the growth again, okay? So let me introduce you, this is the growth. I can skip it because later on I have the rule. I have the rules here, okay? This is the illustration of the rules. Now what is the rules? We have a two version. The first version is an old version. How to pronounce it? I asked some of the people. This is a lake in the United States. It's called Tahoe. That's not English. Tahoe. This is supposed to be some foreign languages. Okay, so this lake name is to name the version of TCP. There's a version of TCP. This version controlling the congestion control rule. Now we have many names. TCP Vegas, TCP Illinois, TCP whatever, many place name, okay? They describe different kind of congestion control, okay? CHK has one invention, okay? Later on I can show you what is that. It's not called TCP CHK, okay? There's a TCP some other names, okay? But invented by one of our professors here, okay? I'm not in CS department, it's an IE, okay? One thing. So this TCP Tahoe is by VJ, by Van Jacobson, okay? And his invention is like this. First, we have some initialization value, very important. The initialization value of CWND is 1. Slow start, really slow. Start with small value. Every time, if we have a CWND smaller than a slow start threshold, yeah, okay, this is a variable name. Smaller than this, every time when we have a successful comeback ACK, the grand effect is as if we have timing 2 to the current CWND value, right? Because when I send 2 packets out, I will receive 2 ACK coming back, and each ACK will generate 1 bonus score, make it into 4. And then make it into 8, make it into 16, so on and so forth. So the grand effect is per round trip time, I can double my bandwidth. Okay? Then what is TCP Tahoe? Tahoe, the characteristic is highlighted in rule number 3. Okay, so let's go to rule number 2. Okay? Rule number 2 says that if the CWND grows beyond the slow start threshold. Go beyond the slow start threshold. It will enter so-called congestion avoidance phase, and each round trip time will generate only one extra packet. So what is the meaning? The meaning is the previous equation. The previous equation say that every ACK, when it come back, it will generate 1 over CWND. But I send out, let's say CWND is 5. I send out 5 packets. And all 5 packets come back. How many bonus I get? 1 over 5 times 5. Every time I send out 5 guys, all 5 guys come back, and every guys will generate 1 over 5. Approximately 1 over 5, because it starts growing a little bit by a little bit. Okay? I have 5 guys, every guy generate 1 over 5, so together it's 1. Okay? Together is 1. So then, rule number 2 can summarize the results. After 1 battery time, I will get 1 bonus CWND slot. So this is not something interesting. The most interesting and the signature of TCP Tahoe is when the loss happens. When's the loss happen? When I sense that there's a missing ACK. Now the penalty is crazy. What is the penalty? CWND equal to 1. Reset the whole CPU is free. You poke for some bandwidth, you are in a 1 GB network data link. You grow, now I just close to 999 megabit per second. Because I'm doubling it, 999 double is more than 1 GB. Then TCP say that, oh, it's congestion. Okay, I'm very afraid of congestion. Let's reset the flow. Let's reset back to 1. Oh, are you crazy? No, it's not crazy. Look at this SOSA threshold. What is SOSA threshold? Because your previous attempt is too great, it's 999 times 2. What is the meaning? 999 times 2 is not a good number. 999 is a good number. Understand what I mean? Previous CWND I said is 999. Still good because it's 1 gigabit per second. 999 megabit now. You multiply it by twice, you are too aggressive. So I tell you, 999 times 2 is not a good number, but 999 is a good number. So 999 times 2 is not good. I divide 999 times 2 by half. So that's 999. Right? Because I know that 999 times 2 is too great. Divide by 2, still good. Because my previous rule is multiplication of 2, or factor of 2. So that means that I keep track of my previous CWND state. So that's why Van Jacobson is a genius. With this simple rule, we can explain so many things. We know that previous step state is good. Multiply by 2, not good. We send it back to previous step, yet. If you grow beyond that, never do this. Never go beyond this, because this is a previous good shape. Previous good network shape. I know where it is. Beyond that, don't grow like crazy, but grow like a gentleman. Grow with a flat style. So this is Van Jacobson prevention, the congestion control. You still grow from the bottom of the flow, and because the CWND is, let's say it's 999 now, 999 times 2 and divide by 2, make it into slow start threshold, you can still have a chance to grow fast. Yet, don't go beyond previous good shape. Previous good shape is too good. Stay there. Beyond that, go to rule number 2. Understand? Now, I ask you one problem. One thing that I didn't mention, the initialization value of slow start threshold. What is that? I only say that a very big value. In Linux kernel, it is 0x8f. Why I need such a big number? Why I need such a big number? Any idea? I want to grow. I want to grow. When the flow just starts, no one knows the bandwidth. I don't know whether out there is a gigabit Ethernet or a satellite network. No one knows. Maybe the satellite network, wow, a huge resource, huge bandwidth, okay? That's why don't limit the growth. Don't limit the growth. And in the Linux kernel, it says the SOSA threshold must be a huge value so that every flow have a chance to grow to any limit that it wants, no matter it is a local LAN, local Ethernet, or a local host network. Yeah, the network inside your machine. Okay? No one knows what's the limit. Let's grow. Grow until you hit certain limit, generate a loss. Then I know where SOSA thresholds should be. When I should stop the exponential growth. Okay? Any problem? Yeah, I guarantee that this is on final exam. Okay. Every year I ask this kind of questions. Yeah, Web Jacobson invention is containing tons of insights, but only 3 simple rules. Yeah, see his power, not by me, okay? I'm only the one who explain to you, okay? His invention contains tons of insights. No problem? Then we go to the next version. TCP Reno. TCP Tahoe is by VJ. VJ think that it is the best thing in 1988. But 1 or 2 years later, some people complained. What is the point that is about the bad thing of the TCP? Why it is this? No one wants to reset the flow, right? I hit certain bar. Why you want me to reset? Okay? So then people suggest one change, and Ben Jacobson adopt to it. The changes also by VJ is to introduce rule 3 and 4. Rule 3 and 4 is a evolution from rule 3 of TCP Tahoe. What is the evolution? It separates 2 kinds of network loss effects. Okay, there are 2 types of events. One network loss event is generated by a timeout. I lost everything. I lost all the ACK. Then I find a timeout. Another loss event is a fast visualization. Still remember what is fast visualization? I lost one data. I lost one piece of data. And the other side complains by sending me duplicated acknowledgement. Complaint will be, hey, lost something. Hey, retransmit. Okay? Ask for retransmission by sending duplicated acknowledgement. Then VJ think that this is not as severe as this guy. Why? Because this guy, you lost everything. Time out. You lost everything. Here, it's not losing everything. You only lost one data trunk. When you collect 3 consecutive duplicate acknowledgement, it is a time for fast retransmission. That means that the congestion is there, but not severe. It's there, but not severe. Here, it's there, and it's very severe. Okay? So this, how can we cope with this? This is the old rule 3. Old rule 3, we think that, oh, there's a very important big event in the internet. Okay, the whole network is down. You have a timeout. Why not reset the flow to grow slowly and we reach the previous state with the SOSA threshold control? Then how about rule 4? Rule 4 is a mild case. I just lost my packet. It's telling that there is a congestion out there. Yet, we cannot ignore this congestion. So, we still fix the SOSA threshold, yet I don't reset the flow. I push it to its previous safe state. Why I said it's a previous safe state? Let me rewind a bit. So, we have a very probably times 2 times 2 times 2. Let's say I times up to 1024. The 1024 still is far something, right? 1024 is rich, still safe. The next number is 2048. 2048 is too big. You have to backtrack to 1024. The rule govern is number 4. And number 4 say that, okay, I know that this is a new slowdown threshold. You cannot grow exponentially beyond 1024. Beyond 1024, go flat. Not the end. I allow you to reset the flow at the same spot of your new slowdown threshold. That means what? That means you climb too fast, I pull you down back to the previous good shape scenario. And you can start that flow immediately with flat growth. So that means what? That means really an evolution. I pull your aggressive flow, become a gentleman, back to your previous safe state, and grow linearly. Not linearly, I mean flat rates. Any problem? This is rule number 4. Nowadays, we are not using TCP Reno. We are using other variations. Okay, it's called what's the name? TCP cubic. Okay, the growth rate is not exponential, but cubic. Wow, I'm so crazy. Okay, so later on, not later on. Okay, you can do Google search what it is. Okay, no later on. This is my last lecture here. Okay, this is Reno. And Reno is still available in the Linux kernel, okay? You can turn on Reno, okay? If you want to try, okay, you can ask me. And this is the comparison I copied from both our textbook. What is Tahoe? This is Tahoe, this is Reno. So there's from the reset point and grow again. Yet, if it is a small or mild congestion, I will start with my previous good shape and grow again. Any problem? No? No? Then this is just an explanation of what I just said. Okay? The severe version, the mild version. Okay? So why we reset the whole flow? Because it's very, very severe congestion out there. Okay? So I can skip this, and this is the summary of this two congestion control. Okay. Now, what I'm going to talk about for the last point, I said I need to borrow extra 15 minutes from you guys because I want to use this TCP congestion control to tell you one thing: TCP is a fair guy. What is a TCP? Is a fair guy. Because of this TCP Reno or TCP Tahoe control, we accidentally generate a fairness issue in TCP. What is it? Let's look at my animation. Okay, so we have two completing flows. Let's imagine that as the case. What is the meaning of two completing flows? This is a big flow already there because of TCP congestion control. It keep growing, and become a very big flow. And there is a young flow, a new flow just start. When it just starts, the flow is small. Now the problem is, there is already big flow here, and the bandwidth share is all belong to this big flow. How can this small flow take the share from the big flow? Right? Understand what's my issue? The issue is your sister already doing BT. Sister selling the BT. Sister watching Korean movie. Okay? And you want to start BT. How your BT beat right? Yeah. How can your BT beat huh? Can it be possible? If not possible, then your sister wake up, okay, and turn on a Korean movie and never stop, right? And take all the bandwidth, okay? Or your sister find that you're doing BT, shut down your computer, right? This or you do the other way around, and you find a sister doing a Korean movie, shut down her computer, okay? Now, how can we beat the big flow? TCP congestion control will guarantee fair share between these two guys. But how? Very easy. So what is this figure? Or this graph? This is a very simple graph that you learn from the secondary school. This is the linear programming. This is called linear programming. The linear programming graph. Okay. So what is it? The color region is the possible resource allocation point. Possible allocation point. What's the meaning? Let's imagine that there is I don't know the real bandwidth. Let's imagine that there is a bandwidth limit called R. We have a small flow, we have a big flow. Okay? So what is the possible allocation point is all point within this region. Maybe you give all the resources to the big flow and a small flow gets zero share. No problem. Right? Because it's just the start of the story. You will have a very strong big flow versus a young just start flow. Okay? Let's say this red dot is my illustration of the particular moment of the resource allocation. And what is this red line? The red line is fair share happens at that moment of time. Right? When the big flow and the small flow share the same amount of resource, then you will go through this line. Okay? And this line is the limit. This line is the limit when x plus y equal to r. Okay? Now, what is the story? The story starts with this allocation point. This allocation point. Let's say the bandwidth is not saturated by the big flow. It's not saturated. It still has room to grow. Okay? So the small flow using bandwidth popping phase exponentially growing, and the growth is much faster. I mean, growth rate, not the absolute value. Growth rate is much faster than big flow. Let's imagine it's the case. Then you will have an allocation point starting with this point, go like this. When we go in this direction, it means that the small flow keep growing. Yes, the big flow will grow much. Imagine that the case is the big flow is in a congestion avoidance phase, flat growth. Here is a young flow, exponential bandwidth popping phase. Now we touch this point. Touch the resource allocation limit. What will happen? Either one of them will have congestion because you touch the limit now. I don't know who. Let's do a random choice. This guy. The big flow experience congestion. Okay? What will happen? Because of the congestion control rule, I don't know what kind of a congestion control rule is touched. Maybe it's not so severe one. Not resetting the entire flow. You being pulled back by half. So the big flow being pulled back by half. And so happened that the small flow didn't encounter any packet loss. So the small flow keep that allocation at this location. Then imagine that the big flow, because of this congestion, goes with the flat growth rates, or I should say it's not flat growth, it's nearly no growth. How about the small flow? Small flow didn't encounter any congestion, still doing exponential growth. Then what will happen? Go to the fair point. Yeah, of course this is my scenario, so it's go sharp into this intersection point. Maybe the real scenario is not like that. Okay? But we will have a chance to touch that fair point. Now we have a fair share. Will it oscillate? Yes. Because both flow want to grow, especially this small flow. Because this small flow never takes any congestion. So it will still go for exponential growth. When it do so, this small flow will backtrack. Okay? And when it's backtrack, it will go either way. Maybe this way. This way means the small flow takes congestion. Maybe this way, that means the big flow takes congestion. Then you will have an oscillation like this, going here, and then go back and go to here, or go to here, and the small flow get a higher flow, higher gain. It will have congestion and then go back. Oscillation between the spare point. This is the case for two flow. It also applies to three flow, 4, 5, 6, all the way up. There's no limit. Okay? And this is the beauty, and this is totally decentralized. There's no one governing this. No one governing this. All the endpoints using this set of simple rules. Okay? And the resulting effect is fairness, fair share of the thing. And who proved this? Yeah, I think you will be surprised. There is a professor has proved this fairness, and the one who proved it is our current IE chairman. Okay, back in 1980 something, he proved or 90 something. Okay, he proved that fairness. Okay, and that paper is so important that it's considered as a best 10 influential paper in the networking research. Okay, yeah, best 10. Okay, because no one knows. Once when Nicholson invented this rule, everybody that it's contain many insights, very good, very good. But no one knows that this will generate a fair share. Okay, everyone is very happy about this rule, and Daming prove it. Okay, prove it that this is fair. Okay, and with this fair, we will also fairly end this chapter. Okay, this chapter ends with a very good story, and it is something related to network research. If you want to dig in more.